What I'm going to do in this video is go over some of the more routine calculations that I left out in the example. So the first thing we did on slide 9 was calculate the gross moment of inertia. And this is just the moment of inertia that you would calculate using principles from mechanics of materials, ES 2410. And you find the centroid first, and then you find the moment of inertia of each of the individual parts about the centroid, and you do that by using the parallel axis theorem. So the first step is getting the centroid. I've made a table here. I've broken up this T-beam into the rectangular beam 1, shown here. Okay, right here. And then the remaining 2 ears I've combined as one rectangle, and I call that piece number 2. You can see here the area of the vertical rectangle and the area of the ears. I'm measuring Y from the top, so the centroid of that 18-inch rectangle is 8 inches down, and the centroid of the 5-inch flange is 2.5 inches down. And the centroid is the sum of A times Y, all divided by the sum of A. So I add up A times Y, and I divide it, and I get the centroid is 5.16 inches from the top, or 12.84 inches from the bottom. And then what I need to do is from the centroid, so let me see if I can sketch that in, 5.16, so just below the bottom of the flange is the neutral axis. And what you need to do is find the distance D of each of these 2 rectangles from the neutral axis. And I've done that there, 3.84 inches from there to the middle of that 5-inch thick slab, and 3.84 inches from there to the middle of that rectangle 1, and 2.66 inches from there to the middle of the slab. And the moment of inertia of a rectangle about its own centroid is 1/12 base times height cubed. That's right here. Okay. Oops, excuse me. That's right here. Okay, and then AD squared. So A times D squared is right here, the parallel axis theorem, and the total moment of inertia of this is 98.96 inches to the 4th. The reason we need this gross moment of inertia is to get the effective moment of inertia, but we also use it to get the cracking moment. And the cracking moment just comes from stress is my over I, when you solve that for y. And the stress is 7.5 square root F prime C is the tensile strength. We just calculated I. And what's different is the distance to the tension face. So a negative moment, the top is in tension. So the distance from the centroid to the top was 5.16 inches. And you get 65.7 foot kips to crack that beam. And the distance from the neutral axis to the bottom for positive moment, tension is on the bottom, is 12.84, and you get 26.4 foot kips to crack it in positive moment. In addition to getting the gross moment of inertia, we need to know the cracked moment of inertia. And you've had homework on this, but just a quick review. E is 57,000 square root F prime C. That's E of the concrete, and as always, it's PSI in the square root. And so you get 3.12 million PSI as E. Steel is 29 million, and the modular ratio of it, which is E of steel divided by E of concrete, is 9.3. And if you remember, the equivalent amount of concrete for a given amount of steel is N times the area of steel. So in this case, the 1.64 square inches of steel is equivalent to 15.24 square inches of concrete. And if you remember, we assume everything below the Neutral axis is cracked. We're saying 0 tensile strength. And so you have concrete above the neutral axis on the unknown distance C. And you have this steel below the neutral axis, which is equivalent to 15.24 square inches of concrete. The distance to the steel is h minus 2.5, so 15.5 inches. And if the neutral axis is at a distance c, from the neutral axis to the steel is 15.5 minus c. And to solve for c, you just balance about the neutral axis. So the moment of that rectangle is 62 times c. That's the area. And its distance to the centroid is c over 2. The area of the steel, equivalent area, is 15.24. And as shown in the drawing, the distance from the neutral axis to the steel is 15.5 minus c. You plug that into a calculator, solve for c, and you get about 2.5 inches to the neutral axis. And so the drawing is correct. The neutral axis is in the flange. Then you get the moment of inertia. The moment of inertia of this rectangle, if you take the moment of inertia of a rectangle about its base, about the middle is 1/12 base times height cubed, but about the base is 1/3 base times height cubed. So 1/3, 62 times c cubed, right here. And we're going to assume the moment of inertia of the steel about its own axis is 0. So we just have AD squared. There's A. This is a distance from the neutral axis to the steel, and squared. And you add that all up, you get 2,900 inches to the fourth. Note that that's different. The gross moment of inertia was 9,900. Now it's only 2,900. It's almost like a third. You have to do this for that was for the positive moment. This is for the negative moment. And if you remember from the beam, it looks something like this, I think. That was A, B, and C. So we just did B. The crack moment of inertia was 2,900. Now we're going to do A. It's a negative moment. The steel's up in the flange. It was 1.48 square inches. Again, D is 15.5. N times 1.48 is 13.8 square inches of concrete, equivalent concrete. Here is C. We don't know. And now the width in compression is only 10 inches. And again, here you have the distance from the neutral axis to the steel is 15.5 minus C. You take moments about the neutral axis. There's the area. There's Y bar, area, Y bar, solve for C. And you do the same thing for the moment of inertia. 1/3 base times height cubed, A, D squared. And now we get 1928 instead of, so we had 2,900 in the middle and about 1,900 on the left end. And you repeat the process. This is at C. It had more steel over there, 2.37 square inches. You follow the exact same process. I'll post these notes if you want to follow the numbers, but you get 2,700 inches to the fourth. And that's how we calculate the 3 cracked moments of inertia. And then finally, we calculate the deflections using this formula that I found, approximate deflection formula. And this formula is handy because it just takes the moment in the left, right, and middle, and you do this. And so I just put in all the numbers. That's the moment for dead load only. So this is the moment in the middle, left and right. That's the length in feet, and come out to 1450 over EI if you multiply all those numbers out. But the 1450 is in kip feet cubed because L was in feet, so that's feet squared, and M is in kip times feet, kip feet. So the numerator is kip feet cubed. The denominator, E is in KS, kip per inch squared, KSI, and I is inches to the fourth, and so that comes out to kip inch squared. And so you're dividing foot cubed in the numerator by inch squared in the denominator. So to make that work out, you have to multiply the numerator by 12 cubed to change that to kip inches cubed. 1728 is 12 cubed. Here's the E, the 3.1 million PSI. I have to change it to KSI because they have kip feet cubed in the top. Change to kip inch cubed. So 3,122 KSI. And here's that I that we just figured out. We averaged actually the left, middle, and right. I do that in the slides. And that's how I got the 0.14 inches. And then on slide 27, when I calculate the deflection due to dead and live load, I do the same thing. Don't forget that 12 cubed. Here's that 12 cubed. And now these moments here, left, middle, and right, are for dead and live load. And I get that 3452 over EI. I have that 12 cubed to do the conversion. Here's the E, that's the same, but the I has gotten much lower now because it's cracked. And with the addition of a higher moment and a lower moment of inertia, you get a significantly more deflection, 0.6 inches. And then eventually what we do in those other slides is we take dead plus live minus dead to get the live load deflection, which was 0.45 inches. And then, oh, this is not dead. This is, sorry, this is sustained. And the sustained deflection that we calculate on slide 21, what you do is you put the moment due to dead plus 30% of the live, and we say that is the load that's always on the building for the next 5 years. And we get those moments. You do everything the same. Don't forget the 12 cubed again. But this is the I for dead plus live, not the I for dead plus 0.3 live. Because when you put the full load on it, you crack the beam, you get I to come down to 3224. And when you take 70% of the live load off, the beam doesn't uncrack. Once it's cracked, that's the moment of inertia. And that's how we get the 0.35 inches. Okay, so those are all the details that I skipped in the example videos, which were long enough. But if you just wanted to know where I got all these numbers, here it is.